In this video, we're going to make a start on the final topic for this semester. For the next few videos, we're going to be looking at the application of modern portfolio theory in reality. We will see the problems that industry practitioners have encountered trying to apply modern portfolio theory to reality, and we're going to look at their solutions. But before we can do this, we need to go over the basics of matrix algebra. There are going to be two parts to this video. In the first part, we're going to review matrix algebra, and in the second part, we're going to apply matrix algebra to calculate portfolio returns and risk. Why do we have to start using matrix algebra? Previously, when we calculated portfolio returns, it took a long time. We had to multiply the stock returns by their weights in the portfolio and then add up these products. With matrix algebra, we can simplify this problem. Let's step right into what a matrix is. An R by C matrix is a matrix that has R rows and C columns. In this case, we're looking at a 3 by 2 matrix. We have 3 rows and 2 columns. If a matrix has only one row, it's called a row vector, and if a matrix has only one column, it's called a column vector. Now let's review some matrix notation. Consider matrix A. It's our 3 by 2 matrix. We can calculate something called the transpose of A. The rows of the original matrix become the columns of the transposed matrix. So if we think about our A matrix here, the transpose, we're going to have the rows, so row 1 is here, it's going to become the first column. So if column 1 is going to be 1, then 4. Column 2 is going to be 2 and 5, and column 3 will be 3 and 6. That is the transpose of A. We will use transposes a lot, so please get used to this notation. You can add and subtract matrices, but you have to be careful because you can only add and subtract matrices if they have the same dimensions. If we have matrix A, it's a 3 by 2 matrix. You can only add or subtract other 3 by 2 matrices. Let's consider an example. If we want to do A plus A, we know we can do this because A and A obviously have the same dimensions. They're both 3 by 2 matrices. What we do is we take row 1, column 1 of the first matrix and we add it to row 1, column 1 of the second matrix. We then take row 1, column 2 and add it to row 1, column 2 of the second matrix. And we do the same for all the elements of the matrix. We can do this now. A plus A is going to give us the first row 1, column 1, we're going to have 1 plus 1. Row 1, column 2, we're going to have 4 plus 4. We're going to have 2 plus 2, 5 plus 5, 3 plus 3, and 6 plus 6. If we do these calculations, we're going to get 2, 4, 6 in the first column, and then 8, 10, 12 in the second column. We've just added two matrices together. Now suppose we've got matrix B, and this is a column vector. It's a 3 by 1 column vector. We can't do A plus B or A minus B because A and B do not have the same dimensions. While we will occasionally use matrix addition and subtraction, what we'll use much more frequently is matrix multiplication. Now we have two matrices here, P and Q. First of all, what would we call P? What's the terminology for P? P is a row vector. It's a 1 by 3 row vector. Q is a column vector, and that's 3 by 1. 3 rows, 1 column. We want to calculate P times by Q. The question is, how do we do that? Let's just line these up. So we've got 1, 2, 3 in matrix P, and matrix Q we have 6, 4, 5. How do we do matrix multiplication? We're going to multiply the corresponding elements of P and Q and then sum them up. When I say the corresponding elements, element 1 of matrix P will be multiplied with element 1 of matrix Q. Element 2 of matrix P will be multiplied by element 2 of matrix Q. And finally, element 3 of matrix P will be multiplied by element 3 of matrix Q. And we add up these products. What do we get? We get 1 times by 6 plus 2 times by 4 plus 3 times by 5, which equals 6 plus 8 plus 15, which equals 29. That's how we do matrix multiplication. But the example we've just considered is relatively straightforward. We've just considered two vectors, a row vector and a column vector. What about for more general matrices? When can we do matrix multiplication? Let's define D, matrix D, to be an M by S matrix. M is the number of rows, S is the number of columns. And then matrix E is an S by K matrix. Here S is the number of rows and K the number of columns. We want to calculate matrix F, which is going to be D times by E. If we write out the dimensions of the matrix multiplication, matrix D is an M by S matrix, and matrix E is an S by K matrix. Whenever you want to do matrix multiplication, the first thing you do is write out the dimensions of the multiplication. Then you can quickly see if it's possible to do the multiplication. You can only multiply two matrices if the number of columns in the first matrix is equal to the number of rows in the second matrix. If those two things are equal, you can do the matrix multiplication. If those two things are not equal, you can't do the matrix multiplication. The other good thing about writing out the dimensions of the multiplication are that we can also work out what the dimensions of F will be. Here we have matrix D and matrix E, and we know that we can do the multiplication because the number of columns in matrix D is equal to the number of rows in matrix E. But what's really neat is that we also know the dimensions of F. The dimensions of F will be given by the number of rows in matrix D and the number of columns in matrix E. Now let's work through a slightly more complicated example. We've got two matrices, matrix D and matrix E. The dimensions of matrix D is that it's a 1 by 2 matrix, while matrix E is a 2 by 2. We want to calculate matrix F, which is going to be D times by E. Can we do that matrix multiplication? Let's write out the dimensions. D is 1 by 2, and that's going to be multiplied by E, which is a 2 by 2. We can do this multiplication because the number of columns in matrix D is equal to the number of rows in matrix E. The dimensions of F is going to be a 1 by 2 matrix. Let's do this calculation for F, which is equal to D times by E. First of all, we know that we're going to get a 1 by 2 matrix as a result of our multiplication. How does this work? The first element of F is going to be equal to 1 multiplied by 3 plus 2 multiplied by 4. So we do rows multiplied by the columns. Let's do that now. 1 times by 3 plus 2 times by 4. What about the second element of matrix F? The second element is going to be the 1 times by 5 plus the 2 times by 6. If we do those calculations, we get 11 and 17 are the two elements of matrix F. That's matrix multiplication. Another common trick that we use when we're dealing with matrix algebra is matrix inversion. When we're dealing with numbers, there are two very important properties that we use a lot without even thinking about it. The first property is that A times by 1 is equal to A, and 1 times by A is equal to A for any number A. The second property that's useful is that A to the power minus 1 times by A equals 1. And similarly, A times by A to the power minus 1 is also equal to 1. Remember that A to the power minus 1 is just equal to 1 divided by A. These properties can also be extended to square matrices. Suppose we have matrix A. It's a square matrix. If we multiply that by matrix I, and I is going to be defined as an identity matrix. This is the equivalent of 1 when we're dealing with numbers. I, an identity matrix, just has 1s in the diagonal elements and 0s everywhere else. So if we multiply A by the identity matrix, we get A. Similarly, if we multiply the identity matrix by A, we also get A. Now suppose we see matrix A to the power minus 1. What does that denote? In matrix algebra, matrix A to the power minus 1 would be called, matrix A to the power minus 1 would be called the inverse of matrix A. And what happens if we do A inverse times by A? Well, we recover the identity matrix. We've seen the identity matrix already over here. Similarly, if we do A times by A inverse, we also get the identity matrix. These properties are going to be very useful. You do not need to worry about how we calculate the inverse of a matrix. Excel will do this for us. Just understand what the properties are and what the result will be if we do A inverse times by A, or if we do A times by the identity matrix. That's all you need to know about. That's the end of the review on matrix algebra. Please make sure you're familiar with everything we've covered, because we're going to be using this in Excel. So it's very important that you know what's going on. If you get lost now, it's very difficult to recover.